Hello. Sorry guys, just had a bit of a technical issue, so had a bit of a delay. So I'm Lisa. I'll be presenting today's 1-for-1 workshop. So could you guys say something in the comment section so I know? Yeah, sorry for the delay. Okay, cool. So today's the algebra section. So for the first hour, I'll be doing introduction to vectors, vector geometry, complex numbers. So just introducing some fundamental concepts and going through some past exam questions. And the last two chapters, Joanna will go through them in the next hour. Yep, cool. So yeah, we'll start with algebra. I think the slides, Gordon will upload them later, I believe so. Okay, so we'll start with algebra. So just some fundamental stuff. The definition of parametric form of a plane is shown here, so definitely great to memorize them for the actual exam because it's just pretty fundamental, and I believe you can get it on the Facebook page. I think Gordon made a essential formula sheet, so you can probably find it up there as well. So we'll start with a simple question. Find the parametric form of x2 plus 6x3 equals to -1. So this is one of the most simplistic questions, which we just need to convert the Cartesian equation of a plane to the parametric form of a plane. So even though x1 is not involved in the question, we still need to consider x1 and take x1 into account. So first we just let x1 be lambda 1, and then we're trying to find x2 in terms of x3. However, we can't just say x3, right? So we have to let x3 be lambda 2, and then express x2 in terms of lambda 3. So we're just trying to convert everything into the form that we just that's given in the definition. So we're trying to solve. So solving x2 just gives x2 in terms of lambda 2 is just -1 minus 6 lambda 2. And then what we do is we just now the vector form of x is just x1, x2, x3, and you just plug the components that we found in the first part in. So then x1 is just lambda 1 as we set lambda 1 x1, and then x2 is just -1 minus 6 lambda 2, which we found here. And then x3 is just lambda 2, which we set. And then we just convert everything into this format exactly as the definition. And note that where lambda 1 and lambda 2 are all real numbers. So this is just a very fundamental question, and in the exam they might go the opposite way. They might do something like find the Cartesian form of a parametric vector, blah blah blah. You just do the opposite way. So yeah, pretty simple, I would say. So moving on to planes. So question 2 is from the MATH1131 2015 paper, where we have to consider the 3 points A, B, C with position vectors 1, 1, 4, 2, 1, 1, -1, 4, 3. And then what we do is we're trying to find the parametric vector form for the plane pi that passes through the points. So for this type of questions, if you're confused, like how does like the 3 points correlate to the plane? I would say it's better if you draw maybe a little diagram, so then you kind of know what you're doing. But if you're like, good enough, then I don't think you need that. But yeah, so if you think visually in a geometric way, if there's 3 points and we're trying to find the parametric vector form, we're first trying to consider what are the position vectors and what are the direction vectors, right? So position vector can be any point, so it can be OA, it can be OB, it can be OC. And the direction vectors are actually it can be AB or BC, because as you can, if you think visually, a line formed by AB is still parallel to the plane, right? So what you need to do is just basically you first let OA be the position vector, which is given the question, so A is just 1, 1, 4. And then you try to find AB and AC as they are the direction vectors of the plane. So yeah, so you just do AB equals to AO plus OB, and then it's just 2, 1, 1. This is the vector of B, and minus the vector of A, and you get 1, 0, minus 3. Same with AC, this is a similar case. And then by definition, given from here, you just convert it into that form, which is position vector plus lambda 1, direction vector here, and lambda 2, direction vector here. So I'll just check if there's any comments. Yeah, I don't think so. Okay, all good. So this is actually interchangeable. So you can let OB be the position vector and find BA and BC. Same for C. So it doesn't matter which point you choose. It just has to make sense. And yeah, I chose OA because it's easy. Do we need to check AB and AC aren't parallel? No, you don't need to, because the 3 points lie on the same plane. So this is you just trying to find the parametric vector form of the plane. So it just needs to be parallel to the plane. You don't need to prove that AB and AC aren't parallel. Yeah. Okay, cool. So moving on. Now we're trying to so cross product is pretty important in terms of 1131 and 1141. So this is one of the new things that we learned in the first year uni course. So cross product is pretty straightforward. You can also find it in the formula sheet. So when A times B is just, you simply you don't need to memorize the formula, I would say. You can just actually cover, so how to find the first row. You just cover the first row of A and first row of B, and then you just do cross. So it's just A2 times B3 minus B2 times A3, which is the first row of the formula. And then the second row, how do you find the second row? You just cover the second row of each vector, and then use the cross product as well. But just one note, for the second row, you have to minus the whole thing by you have to times the whole thing by -1, which you get the second row. And then the third row is, you do the same with the first row. Yep. And then this is a question, I think, in the MATH1131 paper. So formula sheet, I think it's on the Facebook page. On the Facebook page, I think. They uploaded something onto the Facebook, so check out the Facebook page. So for this question, we consider the plane P with parametric vector form, blah blah blah, where lambda 1, lambda 2 are real numbers. So is vector C orthogonal to P? So for this question, you can actually use several different methods. So on Facebook, so for the first method, you could do something like, you can through dot product, you can actually find whether if vector C is perpendicular to each direction vector of plane P. So you could do dot product. So whether if 1, 2, 1 dot product 1, 1 minus 3 is 0, and also 1, 2, 1 dot product 3 minus 1, 1 minus 1 is 0, then you know that vector C has to be orthogonal to P. Or you can use another method. So an alternative will be using the cross product. So you can actually find the normal to plane P, which is just the cross product of the two direction vectors given from the question. So what you do is you cover the first row, and then it would be 1 times -1 plus 1 times -1 minus 3 minus 4 you get, and then you cover the second row 1 times minus 1 plus 9 times minus 1, so minus a, and then same thing for the third row. And note that the normal to the plane is actually minus 4 times the vector c. So you know, since it's a multiple of vector c, you know that c must be parallel to the normal of the plane, right? So therefore, if you think visually, then plane P will obviously be orthogonal to C. So this is just an alternative to the first method that I talked about. You can use either of them and it should all be correct. Perpendicular, yeah. Yep, okay. So, yeah. Okay. Moving on to question 4, finding the distance between a point and a line. So you can actually have several alterations to this question. You can actually, I think in the 2020 paper, it was something like find a distance between a point and a plane. I'll talk about it a little later, so we can just go through this question first. So this is in the notes section of Algebra, so find the shortest distance between point 11 to minus 1 and the line of intersection of the planes. So the first thing that you immediately notice is that you're trying to find the line of intersection of the planes, right? And note that they actually already give you x. So what do you do when you first try to find a line of intersection? What you do is you try to substitute x into the first equation, right? Because you're trying to find the line of intersection. And then you can do the projection and all sorts of other stuff to find the distance. Note that the shortest distance is actually the perpendicular distance between the point and the line. And yeah, so we'll go through the line of intersection first. So as I said before, you substitute x into the equation here. So then you do the dot product and then you expand, and then basically it's just 2 lambda 1 plus 3 lambda 2 minus lambda 1 minus lambda 2 plus 6 lambda 1 minus 9 lambda 2 is 0, and then you do you simplify everything, and then you actually get lambda 1 equals lambda 2. And then what you do is very simple. You just substitute lambda 2 into lambda 1. So it would just be lambda 1, 2, 1, 2 plus lambda 1, 3, 1 minus 3. And this is the line of intersection. Okay, now you have the line of intersection. You're trying to find the shortest distance between the line of intersection and the point. So you can actually use this formula. It's pretty helpful, the one that we learned in high school. So the shortest distance would just be the point minus the projection of the point onto the direction vector of the line of intersection. Note that this formula you can actually swap it around. So it could be projection OA onto V minus OA. Since you've absolute value it, so it will always be positive, so it doesn't matter. So what I'm doing here is I'm preparing for the stuff that I'm gonna do a bit later, so I don't have to make a whole fuss here, so it doesn't look ugly. So yeah. So then we just plug into formula OA. We define OA here. It would just be 11 2 minus 1, but in vector form, minus projection of OA onto V. So this is the formula here. Oh, sorry. This is the formula here. Oh, okay, whatever. So OA times OA dot product V, which we found in the previous part, is just 60 over V square. This is the same as this actually. So because V dot product V will always be square anyway. So yeah, and it will be positive because absolute value, blah blah blah. And then you just simply sub it in, and then it will be 60 over 30, and then yeah, 11 2 minus 1 minus 2 minus 10, and then minus 4, and then plus 2. So you get 1 minus 2 1, and then absolute value, so it will be square root 1 square plus 2 square plus minus 2 square plus 1 square, and you get square root 6. Yep. So Okay, so moving on to question 5. This is from the 2019 T3 MATH1131 paper. And now we're moving on to finding the distance between the two lines. So first part, given, so let x equals lambda 1, 1, 0, 1, and then we have the line here, the line here, 1, 1, 0 plus lambda 2, 2, 0, 0. And we're trying to find we're trying to show that the lines are non-parallel and non-intersecting. So for the parallel part, we're so we're looking at the direction vectors to see if they are parallel or not, and then intersecting, we can actually just equate the x1, x2, and x3 components and see if there's a solution. If there's no solution, then obviously it's non-intersecting. And if we're trying to find the distance between the two lines, we'll use another formula that Professor Daniel Chen taught us in class. So for part I, clearly we can see that direction vectors, they are not multiples of each other, therefore they can't be parallel, right? So we just simply state this sentence and it's enough. And to check if the two lines intersect, as I said before, we equate the x1, x2, and x3 components. So that is lambda 1 equals to 1 plus lambda 2, and then 0 equals to 1, and then lambda equals to 0. But from the line 2, we can obviously tell there's something odd, because 0 can never be 1. And therefore, we know that left-hand side is not equal to right-hand side. So there is no solution. And hence, the two lines are actually non-intersecting. Now we're trying to find the shortest distance, the distance between two lines. So since they are non-parallel and non-intersecting, we can use this formula right here. Where A1 is the position vector of the first line and A2 is the position vector of the second line. And N is the normal of the to the two lines. So we first find the normal. Normal is just the cross product of the two direction vectors, 1, 0, 1 and 2, 0, 0, and then we just apply cross product, which you get 0, 2, 0, and then A1 is just 0, 0, 0, and A2 is 1, 1, 0 as given, and then we're just trying to find A1 minus A2, and you get this. And same thing, same projection formula, you just use the projection formula and you plug the values in, and at the end you will get minus 2 over 2, and then you absolute value it will just be 1. And note that they might ask you something like distance between a point and a plane, and you actually just do the same thing, because you actually you let A1 be the position vector of the point that they gave you, and you let A2 be the position vector of the position vector of the plane, and then you find A1 minus A2, and then normal will just be the normal of the plane, which you can find by the cross product of the two direction vectors of the plane. So you simply just apply this formula. So this formula is quite universal, and and I think that question is in the 2020 paper. So yeah, you kind of just apply the same thing. Yep. Okay. So now moving on to some complex numbers if there's no question. So this is also from the MATH1131 2019 T1 paper. And so complex numbers, for the part A, you try to use the Morph's theorem to express sine 5x as a polynomial in sine x. And that is to find a polynomial pz with real coefficients that satisfy the equation, and then which you get. So you're trying to find sine 5x in terms of sine x. And then part B is by examining the roots of pz, find exact values of sine 2 pi over 5 and sine 4 pi over 5. So note that you can obviously use part A to find part B, and your answer should be expressed in terms of square roots and rational numbers. Okay, so for part A, we're obviously trying to apply Determinant's theorem. So Determinant's theorem is given here. So for any real numbers, theta and integer n, this, if you expand this, it should be this, cos n theta, plus I sine n theta. So for part A, we're trying to consider the expansion of cos x plus I sine x to the power 5. So we can first apply Determinant's theorem to actually get cos x plus I sine x to the power 5. So it would just be cos 5x plus I sine 5x. And then we also, so this is a 1141 question. Because 1131 and 1141, they're overlapping anyway, so this is a 1141 question, and it's from the complex number section. And we can also apply the binomial theorem to the left-hand side to express, cos 5x in terms of, sine 5x in terms of sine x. So we just expand the whole thing using Pascal's triangle and binomial theorem, blah, blah, blah. And then you just get this whole bunch of stuff. But since there's complex number involved, and there's also complex number involved here, we can obviously see that if we're trying to express sine 5x in terms of sine x, we're trying to equate the imaginary parts from both sides, right? So if we expand this whole thing and simplify, you will actually get, so I'm just expressing everything in terms of real parts and imaginary parts, so I could equate the imaginary parts and find sine 5x in terms of something that corresponds to sine x. So then now we're just equating the imaginary parts from the expansions, and then we find this result. So since that the question is asking compare the imaginary parts, you just equate them. You don't need to compare, I would say. Oh, sorry, this is probably layback. Okay, doesn't matter. So sine 5x equals to 5 cos to the power 4x sine x minus 10 cos square x sine to the power 3x plus sine to the power 5x. So then since the question is asking you to only express in terms of sine x, you're trying to convert all the cos stuff to sine stuff. So cos square x is just 1 minus sine square x, and then cos to the power 4x is actually just 1 minus 2 sine to square x plus sine to the power 4x. So this is all given on the formula sheet, I would say. And then you just plug it in and you find sine 5x in terms of only sine x. Okay, so we have this part. So for part B, when we're trying to find the exact values of 2 pi over 5 and sine 4 pi over 5, we know we have to do something with this result that we found in part A to express sine 2 pi over 5 and sine 4 pi over 5, as they seem to be like roots if we express this in terms of, if we convert this into some kind of polynomial. So then I noticed that if we let sine 5x equals 0 and z equals sine x, we can actually get a polynomial here. Oh yeah. And if we solve for x, we can actually find that z, so x will be sine inverse z, and then it would just be ny applying the properties. So where n equals to 0, 1, 2, 3, 4, it could also be minus 2, minus 1, 0, 1, 2. Doesn't really matter, both works. But I'm just trying to make it positive so it's easier for me to, as you can see, there's 2 pi over 5 here and 4 pi over 5 here. So it's easier for me to get the final result. Okay, so then z will just be sine, plugging in x equals to 0, pi over 5, 2 pi over 5, 3 pi over 5, 4 pi over 5, will just be this result over here. And then, but note that sine pi over 5 is actually just sine 4 pi over 5. if you apply the trigonometric identities. And also, this is a similar case for sine 3 pi over 5. That would just be sine 2 pi over 5. So we know that the sine 2 pi over 5 and sine 4 pi over 5 are like double roots, which would be more convenient for us to find the solution a bit later. So then we can actually take z out and eliminate z, because z will just be 0. And then when we found earlier z will just be 0, we can actually take this out. And then since the only two roots left are sine 2 pi over 5 and sine 4 pi over 5, we can actually apply quadratic formula to find z squared. And yeah, will just be 20 plus minus, so b squared, so minus 20 squared, minus 4 times c, which is 5, and then a is 16 over 32, and you get z squared over here. And you're trying to find z because the only two solutions that are left are sine 2 pi over 5 and sine 4 pi over 5. So then z will just be square root the result we found in an earlier stage over here. But note that sine 2 pi is actually bigger than sine 4 pi over 5. We know that the two solutions are either of these two. And given that we know sine 2 pi over 5 is actually bigger than sine 4 pi over 5, sine 2 pi over 5 has to be the plus case, and sine 4 pi over 5 has to be the minus case. And this result actually, if you think about it, if you draw like a unit circle, you can actually also know that sine 2 pi over 5 has to be bigger than sine 4 pi over 5. And then finally, we are able to express sine 2 pi over 5 and sine 4 pi over 5 as like square roots, I would say. Yes, square roots and rational numbers. I would say probably, I'm not sure though, but this is definitely, yeah, but I would say it probably might be a potential 1131 question. So, okay. Yep. Moving on, are there any questions in the chat box? If there are any, I'll just go ahead. Probably no? Okay. So moving on to also complex numbers. So this is from the 2013 paper from MATH1131. And so the question is just let pz equals to z to the power 4 minus z to the power 3 minus z squared minus z plus 2. And we denote roots of p as a1, a2, a3, where a1 is just integer. And then part A, we're trying to find the value of a1. So I might just go through part A first and then go back, so then you guys don't forget what the questions are. So yep, sure. A1, A2. A1 minus A2 is just minus 1, 0. Where A1 is just the position vector of the first line, and then A2 is the position vector of the second line. Okay. So for question 7, we're trying to find the value of A1, and we can actually just simply sub in a point. And do we maple for this? You don't have to. I didn't, so should be fine. We can actually just simply plug in 1, and then you can actually just get the result, because you always try to plug 1 in because 1 is the most basic one. Difference between position vector. Oh, it's just not the difference, I would say. It's the... So, oh, sorry. Oh, for question 3. Right. Okay. Sorry. Did I skip the part? Oh, sorry. Yeah, cool. So A1 and A2, note that A1 is just a point and A2 is also a point. So if you do A1 minus A2, it would just be the line. Sorry, not the line. It would just be another vector that's connecting the 2 points together. Yeah, you could use maple, but yeah. The maple, like plugging in like numbers, just takes more time. When you can actually just plug in, you can put the numbers in your head and work out the solution. So if you let z equals to 1, it will just be 1 minus 1 minus 1 minus 1 plus 2. So the solution will obviously be 0. So the A1 can obviously be 1. And for part B, given that at least one of the roots of P is not real, deduce how many of the roots are real. I guess you could use maple, but also like some of the questions require a bit of like reasoning. So you could probably think and like just reason it with words. So you know that one of the roots is not real, and you already found that one of the roots is real in the previous part, and there's 4 roots. And complex roots always come in conjugate pairs by the conjugate theorem. So P has real coefficients. So therefore, P cannot have like 1 non-real and 3 real roots because it has real coefficients, so it doesn't work that way. Or like 3 non-reals and only 1 real root, or 4 non-real roots, because that would not work given that we already found that A1 is a real roots. Therefore, there must be 2 complex roots and 2 real roots. So yeah, so there's 2 real roots. So for part C, by considering the sum of the roots or otherwise, prove that at least one of the roots has a negative real part. So we found that A1 is a real root, and for the start of the step, we assume that A2 is the second real root, so therefore A3 and A4 has to be the conjugate complex roots, right? And A1 plus A2 plus A3 plus A4, you can actually find that by using the sum of roots. That would just be minus b over a, so minus 1 over 1 is still 1. So the sum of these roots will still be 1. And given that a1 is 1, we could actually convert that. So a2 plus a3 plus a4 would just be 1 minus 1, so you get 0 over here. And note that a2, a3, and a4 are conjugate complex roots. You can actually cancel the imaginary parts, so all that's left will be the real parts times 2. So where we express x as the real parts of x3 and x4. A3 and a4. So a2 plus 2x will be 0. So when we have this result, we know that something's positive and something's negative, right? Otherwise, how can we get 0? So therefore, we know that either a2 has to be less than 0 or 2x has to be less than 0. So we are able to get that at least one of the roots has a negative real part. So a3 and a4 might have a negative real part, or a2 might have a negative real part. Yep. So these are the possible cases over here. And then moving on to the last part, which is, I would say, the hardest part. So prove that the absolute value aj is greater than half for j equals to 1, 2, 3, 4. What I would do is I would prove by contradiction. So we first suppose that the absolute value of aj is actually smaller or equal to a half, which we found here. So, and then a is a root that satisfies the polynomial. So PA will just be 0. And then if we sub it into the given polynomial, we will just get a to the power 4 minus a cubed minus a squared minus a would be minus 2, because PA would be 0. So we're moving the 2 to the right hand side, so we get this result. And this just gives, if we absolute value both sides, so a to the power 4 minus a cubed minus a squared minus a will be absolute value minus 2 will be 2. And here we're just applying the triangle inequality. I think that's the name. Where this absolute value will be less than the absolute value of the whole thing. Sorry, that's a plus here. Sorry, just a bit of a typo. Yeah, okay, typo here. Sorry, guys. And so it will be the sum of everything. So ignore the minus here. Will be plus, 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 plus. And then since we know that a is actually smaller or equal to a half, we we raise it to the power 4, so it will be 1 over 2 to the power 4 plus 1 over 2 to the power 3, and then you do the same thing for a2 and a. And when we add them together, it will be 15 over 16. And this is obviously not greater or equal to 2. So you know that there's some problems and this is a contradiction. So therefore, this does not work. We know that aj has to be greater than a half for j equals to 1, 2, 3, 4. So this is proven for this part. Yep. And yeah, I think this is okay. This is pretty much it. So I'll fix that part up before Gordon uploads onto the directors upload them onto the website. Yep. So any questions? Or because I think my part is pretty much done, and then it's Joanna's part. So we're able to catch up. Finish at 6, and then Joanna can start her part.
So I just started streaming. Can anyone hear me? Or can everyone see the stream? Yeah, okay. All right, thanks everyone. So, yeah, okay, I'm going to start with my part now, which is going to be chapter 4 and 5, so linear equations and matrices, and the last chapter is just on matrices. As with before, this stream is going to be mostly based on questions from past exams. It doesn't really cover the theory of the course comprehensively, but I will be covering some theory that will be needed in questions throughout this stream. So yeah, first of all, we're going to start off with chapter 4, and we're only going to have one bit of theory here, and it's to determine how many solutions there are to a set of linear equations given a representation of that system of linear equations in row echelon form for a given matrix. So firstly, how do you determine if the system has no solutions? Well, if the right-hand column of the augmented matrix representing the set of linear equations is a leading column, then there's no solution. So what this means is when you have like a bunch of variables up here, they might all be zeros, and you might have like some variables and you have some zero row on the left, but there's a non-zero row, or the term on the right is a non-zero entry. So that's when you know that there's no solution. Sorry. Second point, the system has a unique solution if and only if every column on the left is a leading column. So most of the time, you'll see this as maybe a perfect diagonal of leading entries. And you have like stuff here, and you'll have like numbers down here. So that's one way that you might see that the system has unique solutions. But another possible thing that might happen is that there are zero rows below it. So in that case, the system of, this system of linear equations has a unique solution as well. Final case, the system has infinite solutions. So that's when we might have something that looks like this. Like so. These can be like whatever terms, and this is when the right-hand column is not a leading column, and there's a non-leading column on the left-hand side. So this will be the non-leading column, and if we want to determine the solutions to this set of linear equations, we parameterize the variable corresponding to this column. And so those are the three cases that you'll see with matrices in row echelon form. I hope you guys remember that from the theory that you've learnt so far. But let's move on to some questions. The first question's going to be kind of a warm-up, I guess. And it asks us, for some values of the real parameters a, b, c, and d, the curve ax squared plus by squared plus cx plus dy equals 1 passes through the points a at 1, 1, b at 2, 3, and c at 0, 1. Explain why the following equations can be used to determine the values of a, b, c, and d for which the curve passes through the points. And I guess first question, quite straightforward. So if the curve passes through these 3 points, the coordinates of these points has to satisfy this equation. So the first equation we get from substituting a at 1, 1. Second equation we get from substituting b at 2, 3. And the third equation we get from substituting c at 0, 1. So I've written that in the slides later, but I don't think I need to show that to you yet. But yeah, the next question we want to use Gaussian elimination to solve the system of linear equations in part 1. So I hope you guys remember your elementary row operations, but just in case you've forgotten, we have the possible row operations that we can do are switching to rows, multiplying a row by a non-zero scalar, and also adding a multiple of one row to another. So we want to use these operations to reduce this augmented matrix to row echelon form. And so I guess the way to do it is to get rid of any leading entries of a row that is in the same column as leading entries in the rows above it. So in the case of this matrix, we want to get rid of this term, and so we'll subtract from, to get row 2 in here, we subtract 4 R1s, so row 1s of this matrix from the row 2 of this matrix. So that's like what the notation here is saying. And so now the term disappears, and I guess to make our lives a bit easier, it's always nice to subtract a multiple of 1 from another number rather than subtracting like a fraction. So I switched around rows 2 and 3, and then from there I subtracted 5 of row 2 from row 3 to get the matrix in row echelon form. So as you can see from here, all of the leading entries of a row are further to the right than any leading entry in the rows above it. So we have our matrix in row echelon form. And we have a non-leading column. So that's something to note when we look at the next question, which is, are there 0, 1, or infinitely many curves of the form ax squared plus by squared plus cx plus dy equals 1, which passes through the points a, b, c, and d? And clearly, there are infinitely many combinations of a, b, c, and d. And so there are infinitely many curves that pass through a, b, and c. And we know from before because there's a non-leading column. So next question. Using your answer from part 2, find the parabola of the form y equals to alpha x squared plus beta x plus gamma, which passes through a, b, and c. So this curve that we have here, the only term that's kind of not very, I guess, parabola friendly is the by squared term. So we want to somehow get rid of it. And remember, based on our matrix in row echelon form, we can parameterize the variable d because d corresponds to the non-leading column. So we can set d to be some value and then make every other, make every other variable kind of fit around that. And we want to set d so that b is equal to 0 because b corresponds to this y squared term here, which we don't want. So we look at how we get b to be 0 is we look at this row And we see that b plus d, well, b plus d is equal to 1. And so if we set d to be 1, then b will be 0. And so then we'll get a parabola. So, so as you can see, as I explained above, we let d equal 1. And from this matrix, matrix in row echelon form, we have a plus b plus c plus d equals to 1, and minus 2c minus 6d equals to minus 8. And so just using our algebra skills that I'm sure are all very good, we can deduce from back substitution, so letting d equal 1 and letting everything fall into place there, we see that c is equal to 1, b is equal to 0, and a equals to minus 1. And so then we substitute these values back into the curve, and we get a parabola of the form y equals to x squared minus x plus 1. So that was the first question. I hope that was pretty straightforward, but if there are any questions, please drop them into chat. Let me have a look. Okay, are there any questions so far? I don't see any, so, or maybe there's a delay. I'll look back into chat later, or maybe the directors can answer your questions. But anyways, we'll be moving on to the next question, which was in the 1141 2020 T1 paper, and it involves Maple, our favorite software of all time. So whenever you see like these Maple sessions, it might look a bit intimidating because I don't think anyone really remembers what any of the operations actually do in Maple, but I think they're not going to be very mean and like do something that's completely out of the blue just to test you on whether you remember Maple. They're probably going to use like the process that they follow in the Maple session is going to be very similar to the way that you would solve the they probably just like want to test you on whether you can like reason things mathematically from what you see. So don't worry too much if you don't know what any of these instructions mean, because to be honest, when I went to fetch this question, I didn't know either, but it's pretty easy to like suss out based on what you do when you're like reducing a matrix to row echelon form. Anyways, that was a long ramble, but let's I guess look at these operations. So first thing, they're creating the left-hand side matrix, and then this is the right-hand side column vector, and we're just creating the augmented matrix here. So now let's have a look at what these row operations are doing. So the first thing that I would do if I wanted to reduce this matrix M is that I'd probably switch rows 1 and 2 because I like the one term being the leading entry. So this command, I suspect, means switching around rows 1 and 2. And this seems pretty logical, like based on what I see as the inputs. So next, I would want to get rid of what's now the M term in the second row. So how I do that, is I'd subtract m times r1 from r2 to get the new r2. Next, based on how I sussed out the instructions earlier, this looks like it's saying that I'm switching, or I'm subtracting 2 r1s from r3, and that would make sense because the leading entry in the entry that's furthest to the left in R3 is 2, and so it would make sense to subtract 2 R1s from R3. So that's a bonus for us because it reinforces the fact that we're probably right when we're sussing out what these row operations mean. Anyways, next, I look at this command and I have no clue what it means, but don't worry because it's a row operation. We have 2 row operations down, and we know that this doesn't look like, well, like the current command that we're looking at doesn't look like any of these. So using the powers of deduction, we can probably deduce, that was really loud, sorry. We can say that this is probably multiplying R3 by R3 by 1 on 2m minus 1. And next, R2, same as how we deduced the instruction from before. R2 is, we multiply it by 1 on 1 minus m. Next, we're probably switching around R2 and R3 because it looks like this instruction here. And then finally, we're adding m plus 1 times R2 to R3 based on what we sussed out from before. So use your deduction skills to suss out all of these, I guess, row operations mean, and you'll be fine. So next, let's actually move on to the questions. So first question, for which real values of m, if any, does the system have no solution? And let's have a look at the matrix, the final matrix that we have here. So there's no solution when this term is 0 and when this term is non-zero. And that's the only case we really have to test because these entries aren't written in terms of m, so we're kind of safe in assuming that there's going to be no 0 row here or here. So in that case, the only value that we can really test is when m equals to minus 3 on 2. And when we sub that in, we find that m squared plus 6m plus 10 is non-zero. And so when m is equal to minus 3 on 2, the system has no solution because there's a leading column on the right-hand side. Next, the question asks, the system has infinitely many solutions when m is equal to 1. For which other real value or values of m does the system have infinitely many solutions? And you might look at this thinking, like, how am I supposed to figure that out? Because clearly, well, like, from this row, there is, like, this is the only row that we can really work with, right? And we found that when this is equal to 0, this is non-zero. So how do they find that case when m is equal to 1? Well, if you look at these, well, I should point the arrows in this way. These two operations, you'll find that the system that M3 represents is different from the one that M7 represents when M is equal to 1 on 2 and when M is equal to 1. Because we can only multiply rows by a finite scalar. And if the denominator is 0, then we're not really doing a valid move there. So we want to check when M is equal to 1 on 2. And we test this value. We substitute that value into M3. And we find that this row becomes a row of zeros. And since this row becomes a row of zeros, and these are like non-zero, this becomes a non-leading column. And there's no leading column on the right because this entry is also 0. So when M is equal to 1 on 2, we have infinitely many solutions as well. So now the question asks us for which real value or values, it should be, or values of M, if any, does the system have a unique solution? And we can suss out the solutions by remembering from before that a system of linear equations either has no solution, infinitely many solutions, or it has a unique solution. And so the system would have a unique solution for every value except when M is equal to 1, where there's infinitely many solutions, when M is equal to 1 on 2, where there's infinitely many solutions, and when M is minus 3 on 2, where there's no solution. So that's our answer for 3. And then for question 4, they want us to let M equal 1 and find solutions of the form A plus lambda V. And they want us to find what A and V are. So as we do, we substitute M equals to 1 into matrix 3. And if we switch around these rows, then we get a matrix in row echelon form. And so just by substituting in the values or the coefficients, or rewriting, I guess, like the set of linear equations from this matrix that we have, we get this set of linear equations. So now we want to represent the solutions as a vector, x1, x2, x3. And we want to parameterize, if we switch around these two rows, we get that this is the non-leading column. So we want to parameterize x3. And so when we do that, we let x3 equal lambda. We can write everything else in terms of lambda. And we get x is equal to this vector. And we can separate the terms out so that all the lambda terms are on the right. I don't know my left and rights. And also, all of the constant terms are on the left. Did I say left just now? Okay, I can't even remember. Anyways, from this, we can see that A is equal to this vector and V is equal to this vector. So we get our solution. Next, we're going to be moving on to chapter 5. So, and I'm going to provide some more reminders of the theory that you might need to know. So firstly, I hope you guys all remember how to calculate the determinant of a 3 by 3 matrix. So the idea is that we take the first term, we multiply it by the determinant of this matrix here. We take and then from that we subtract the second term times the determinant of this matrix. The 2 by 2 matrix formed by these entries. And then we take the third entry in the first row and we multiply it by the determinant of this matrix here. I don't know why I'm so out of breath. I feel like I literally just been talking. I might be like very unfit, but anyways. So another way of calculating the determinant of the matrix, which you might not remember because it was like mentioned, I think, in chapter 1, where determinants weren't really a thing yet, that the determinant of a 3 by 3 matrix can be calculated by taking the scalar triple product of the 3 row vectors. And this is a very cool property that we'll be using later, so that's why I put it here, even though I don't think it's very often mentioned. Okay, anyways, so next reminder, the relationship between determinants of a matrix and the solubility of the linear equations that we form. So if the determinant is non-zero, then the equation, the equation ax equals b has a solution, and the solution is unique for all b. So remember, we're trying to find out what x is here, so it's like a solution in terms of x. And next, if the determinant is 0, then this equation either has no solution or an infinite number of solutions for a given b. So now let's move on to our next set of reminders. And these are like the really cool things about determinants that somehow in the most unlikely places answers the questions, which we'll see later. But yeah, so here are some properties of determinants. Once again, doesn't cover like all of the properties that you've learnt in the course, but just the ones that we'll be using in our later questions. So suppose that A and B are 2 n by n matrices, then the determinant of their product is equal to the product of their determinants. Next, if A is an invertible, A is an invertible matrix if and only if the determinant is non-zero. And you might see a connection between this property and this property. So if a matrix is invertible, then this system has a solution and the solution is unique. So yeah, that's a connection. Next, if a row or column of A is multiplied by a scalar, then the value of the determinant is multiplied by the same scalar. So if, say, a matrix B is obtained from the matrix A by multiplying a row or column of A by the scalar lambda, then the determinant of B is equal to lambda times the determinant of A. Okay, anyways. So now let's use that knowledge to answer some questions. So we want to consider the n by n matrix B and a vector y such that by is non-zero and b squared y is 0. And we want to find a non-zero solution to this system. And we can see that we can write b squared y as b times by, and we know that that's equal to 0. And nicely enough, by is non-zero, and so a solution would be by. So a non-zero solution to this system would be by. And you can kind of check that this is by is a column vector just by considering the sizes. So we have a matrix of size n by n, and we have a column vector of size n by 1. So our final solution should be taking the n here and the 1 here to get our final size. Anyways, that's like a little sanity check to make sure that we're not completely going off in the wrong direction. So yeah, anyways, that was a long ramble. The solution, a non-zero solution, would be by. Next question, what can be said about the determinant b? And I guess we can see that for this system, one solution is the zero vector. And we also see that there are two solutions because there is a non-zero solution to this system. And so what that means is, remember from before, a system can only have, or a system of linear equations represented by this matrix can only have a unique solution, no solutions, or infinitely many solutions. And so what that means is this probably has infinitely many solutions. Well, it does have infinitely many solutions. And so the determinant would have to be 0. Or like you can also argue that the solution is not unique, so the determinant can't be non-zero. But yeah, that's our second part. And then now we want to show that the linear system b squared x equals to the 0 vector has infinitely many solutions. So yeah. Previously, we argued that the system of equations has infinitely many solutions, therefore the determinant is 0. Now we want to argue that the determinant is 0, therefore the system has infinitely many solutions. Except we also need to argue that there's not no solutions. And I guess it's quite straightforward because there is a solution to this system of linear equations, and that is the 0 vector. We also know that the determinant of b squared is equal to the determinant of b times the determinant of b, which is 0. So the solution can't be unique, and there's not no solutions. So therefore, the system must have infinitely many solutions. So yeah, that concludes this question. I've written it out more nicely in question, like in this solution here, but feel free to read it later because yeah, I think that covers, the explanation covers it. Next question, we want to find the determinant of this 3 by 3 matrix, and it should be pretty straightforward because we're simply just like plugging it into the formula and factorizing to get our final solution. I think there was a mistake in the paper because I was doing this question and it asked us to show something else. I think it asked us to show that it was T1 minus T3 or something like that. And I wrote like the calculation for this determinant out 3 times. And each time I got this. So therefore I conclude that the paper was wrong. But I don't know. Maybe you guys can go through this question and check for me. But yeah, I hope that this is the right thing. Anyways, this isn't the interesting part. So the next question, we want to suppose that T1, T2, and T3 are distinct real numbers and prove that for any set of alpha, there is exactly one polynomial PT of degree less than or equal to 2, where PTI equals alpha I for these values of I. So 1, 2, or 3. And I guess like you can kind of like get an intuitive idea of how you're going to do this problem. So we know that T1, T2, and T3 are distinct. So that means that T1 minus T2 is non-zero, T2 minus T3 is non-zero, and T3 minus T1 is also non-zero. So that kind of tells us, I guess, that the determinant is non-zero. And so we know that a system of linear equations represented by this times some vector x equals to some vector b must have a unique solution. But how are we going to represent that as a matrix? So let's kind of consider what set of linear equations we can form given PTI equals to alpha I. So suppose that we can write PT as AT squared plus BT plus C. And by substituting PTI equals to alpha I for I equals 1, 2, and 3, we get the matrix that we saw before. We get this vector, and this vector is essentially representing the set of coefficients that PT will have. And alpha 1, alpha 2, alpha 3 are just the variables that we have, or the values that we have on the right-hand side of the linear equations. So now we determined from before that any vector, say like, let's just say call this vector like x or something, any vector multiplied by this determinant equals some other vector, this set of linear equations must have a unique solution. And so therefore, or a unique solution in terms of x. And so therefore, this set of coefficients must be unique. And yeah, we reason that out because the determinant of A is non-zero. So, so since the set of coefficients has to be unique, then the polynomial has to be unique as well. And it's actually, I guess, what was I going to go with this? So something that I wanted to mention is that the degree of this polynomial is less than or equal to 2. And so, and the reason why is because A can be 0. So that's why we have degree less than or equal to 2 rather than just a degree that's 2. But that's just a side note. We don't really need to think about that. So now, moving on to our next question. Oh no, my screen's frozen. Oh, okay. We want to let A and B be two non-zero and non-parallel vectors in R3. And let A be the matrix with rows A, B, and A cross product B. Show that the determinant of this matrix is equal to the modulus of the cross product of A and B squared, and determine whether or not A is invertible. So let's use that handy little fact that I found in chapter 1 of the notes, that the determinant can be written as the scalar triple product of the 3 row vectors. And so I guess like this is what it would look like if we wrote it out. But how I got from this line to this line is that it doesn't matter what order you take the, I guess like where you put the cross and where you put the dot, as long as you don't rearrange the vectors. So if we have like a scalar triple product that looks like this, we can write it as A times B. Oh, not A times B, A cross product B time, not times, dot product with C. So yeah, so we can write it like this. And as you can see, that's exactly what I'm doing to get from line 1 to line 2. And easily enough, this is the dot product of a vector with itself, which is equal to the modulus squared. And so we've proven we've proven what we were asked to prove. And so now we want to determine whether this matrix is invertible. And the cross product of 2 vectors is 0 when either one of the vectors are 0 or when they are parallel. And since we're guaranteed that they're non-zero and not parallel, we can say that their cross product is non-zero, and so the determinant is non-zero, and that means that the matrix is invertible. So that's nice. Now to the next question, which I think might be a bit more challenging. The previous question would be challenging as well if you just didn't know the result. But yeah, the next question I find is a bit of a mental exercise. So yeah, let's go through it. Oh no, I should have bolded this. Losing marks for assignments from not bolding vectors. Anyways, so we let V be in R3 such that V cross product A is equal to B and V dot product A is equal to the modulus of A. And then now we want to write V as a linear combination of A, B, and A cross product B. So, this might look a little intimidating and, but don't worry. So the way that I'd approach this question is I've given these algebraic properties and I can do some little manipulation with it here and there. But I did that for maybe 2 minutes and I realized that I wasn't getting anywhere. So when you find that you're stuck in the same situation, try to think of these two properties or these two facts that we're given. Try to think of them geometrically. So V is equal to B tells us that A and B are perpendicular or orthogonal. So that's something to work with. But if A and B are orthogonal, then that means that A, B, and A cross product B are mutually orthogonal. And we know that, we already know by default that A cross product B is orthogonal to B, and A cross product B is orthogonal to A. But we have this extra fact that A and B are orthogonal. And so what does that tell us? Well, we can decompose V into orthogonal components by taking projections of V onto each of these vectors, and then summing them together to kind of recompose V, I guess. So let's have a look at the solution in words. So as I said previously, since V cross product A is equal to B, A and B are orthogonal. And this means that since, A, B, and A cross product of B are orthogonal, V can be decomposed into orthogonal components by taking the projection of V onto each of these vectors, and then V can be written as the sum of these projections, which will also be a linear combination of AB and A cross product B. So so that's what I do on the next slide. But we're given the fact V cross product A equals B. This also tells us that V is orthogonal to B. So the component of V on B has to be 0. Because, wait, did I say the projection, or did I say, okay, anyway, same thing. So V is, the component of V on B is 0. So anyways, I'm getting short-term memory loss. So anyways, let's now write V as the projection of V on A plus the projection of V on A times B. I guess you could say plus the 0 vector, which is what the projection of V on B is. But now we can use our projection formula. So we have, if we project V onto A, then the projection formula is V dot product with A over A squared times the vector A. So it's A appears, the vector that we're taking the projection on appears in 3 places. That's how I remembered the projection formula, which may not be very mathematically nice, but yes, that's how I remembered it. And applying the same formula to the second part, this is the coefficient that we get. So the coefficient of A, which is lambda 1, we can write that as V dot product A over the modulus of A squared. And we're given nicely from before that the V dot product A is equal to the modulus of A. And so we get nicely our lambda 1. Next, we can deduce what lambda 3 is, given what we have here. And once again, using the fact that we can put the dot and put the cross, we can switch them around. Given we don't rearrange the vectors, we get V cross product A dot B. And nicely enough, we know that V cross product A is equal to B. And so the top part is B squared. So now we have nicely our linear combination of V in terms of A and A cross product B and B, I guess, somewhere. Anyways, next question. This is going to be our final question. So, in this question, A A and B denote invertible n by n matrices, such that AB is equal to minus BA. And we want to show that n must be even. And this might look very daunting because you might be like rummaging through all the formulae that you remember and find that none of them relate to the parity of n. So like, how do we do this? And as I said before, determinant properties come up in the nicest of places. So that's what we're going to be using. So we first note that the determinant of AB is equal to the determinant of A times the determinant of B. And that's nice, we're using a property. And then now we also consider the right-hand side. So remember AB is equal to negative BA. We also consider the right-hand side now. And so we take the determinant and we find that this is equal to the determinant of minus B times the determinant of A. And remember, whenever we multiply a row or column by a scalar, then the determinant of that matrix is also multiplied by that scalar. But we're multiplying here every row by minus 1. And so that means that we multiply the determinant of B minus 1 by minus 1 n times. So well, I kind of did this in an alternative way. You can do that as well. But yeah, that's kind of how I get the minus 1 to the power of n out the front. And so, that's nice. So we have our using the determinant of product equals product of determinants property, we can write this determinant out in this form. So, so using the property that AB equals to minus BA, we see that the determinant of determinant of A times the determinant of B is equal to minus 1 to the power of n times the determinant of B times the determinant of A, which is nice. So now we're kind of maybe a little bit stuck again, but we use the property that they gave us that A and B are invertible. So we're like squeezing out every single fact that we can find from the question and taking advantage of it. And in this question, A and B are invertible. So what that means is their determinants are non-zero. So that means that the product of their determinants are non-zero as well. So if we divide, well, I guess we can cancel out the determinants because we're not dividing by 0. We find that minus 1 to the power of n is equal to 1. And that can only happen when n is even. So that's how we know that n is even. So once again, determinant properties come to save us. Next question. We want to show that B squared is a multiple of the 2 by 2 identity matrix, given that n is equal to 2 and A is equal to this matrix. So I tried to think of a neat solution to do this, but I couldn't really think of one. I just kind of like brute force this. So if anyone can think of like a really nice solution to this problem, maybe share it in chat because I couldn't think of one. Let's have a look at the solution. So I'm just gonna write B as a generic 2 by 2 matrix, so not making any assumptions there. And I'm using the fact that they gave us. So AB equals minus BA. Well, like I'm going to use that fact. So I'm going to calculate what AB is. And doing the calculations, I hope you guys remember. So yeah, like we multiply this term by this term, and we add it with this term added to this term. And we do that for every term. Yeah, so doing that matrix multiplication, we find that this matrix is equal to this. And I want to find what BA is now. So I do the same thing, matrix multiplication, find that BA is this, which is nice. So now I want to equate AB and BA. So let's write that out because I didn't want to pack the slides too much. So I'm just taking the negative of this because this is actually BA, and AB is equal to minus BA rather than BA. So let's write out the negative. And for two matrices to be equal, all of their components, all of their entries have to be equal. So like the entry in the corresponding row and column have to be equal. So that means that, well, the entries of interest is that B11 is equal to minus B11, and also B22, or minus B22, is equal to B22. So that means that these two entries are 0. So I guess that kind of tells us that we can write B in this form. So now if we just apply our normal matrix multiplication by taking the product of B like so, we should get this matrix, which you can see the entries in the diagonal are equal, and every other term is 0. So it has to be a multiple of the identity matrix. Whoops, this should be T. So now let's do the final question. So we want to show that there are infinitely many matrices of the form this, such that its square is the identity matrix. So I guess like the only way to really see that is to take the square of this of a matrix of this form and see what it gives us. So yeah, let's do that. So if we write out, when we're using like, I guess, expanding the brackets of matrix, like stuff to do with the multiplication of matrices, we want to be a bit more careful because we can't just like switch all the matrices, like the positions of the matrices around at will, because BA is not necessarily equal to 8B. Yeah, let's just be more careful. So we use the distributive property, but we need to make sure that every matrix that appears on the left has to stay on the left of any matrix that we're multiplying with in the right. So let's write it out carefully. It's basically going to be like this, but let's, I guess, like talk through it. So we have lambda A from the left bracket and lambda A from the right bracket plus lambda A from the left bracket times mu B from the right bracket plus mu B from the left bracket times lambda A from the right bracket plus mu b from the left bracket times mu b from the right bracket. And yeah, as you can see, that's what I get in this this line. So I guess if you wanted to describe this property, that like, you know, the fact that the matrices on the left have to stay on the left and the matrices on the right have to stay on the right, we call this left distributive and right distributive. So we can still use the distributive law, it's just that we have to make sure all of the matrices that are on the left stay on the left. So yeah, if you ever wanted to like describe that property, then you can use those terms. So now, remember, it doesn't matter when we multiply in the scalar. So that's also a property of matrix multiplication. So we can kind of just bring out all the scalars to the front. And we see here, without switching the orders of B and A, like because we need to make sure we don't do that, we see that AB equals to minus BA. So that means that AB plus BA has to be the zero vector. Or the zero, not the zero vector, the zero, like the matrix zero, like the n by n matrix where every entry is zero. Anyways, yeah, so we have that, and we see that A squared, if we just like quickly calculate what it is. So remember, A is equal to the this matrix that I've written out here, and its square, since it's a diagonal matrix, like with all of its terms, like with only entries on its diagonal, we can write out its like powers as like just powers of the entries in the diagonal. So we get that A squared is equal to the identity matrix, which I've done here. And we also know that B squared from our previous question is a product, is a scalar multiple of the identity matrix. So we can also express it as gamma times the identity matrix for some constant gamma. And so we see that lambda squared plus gamma times mu squared times the identity matrix is equal to this expression here. And for this to be the identity matrix, we want lambda squared plus gamma times mu squared to equal 1. And we can see that for any gamma that we choose, so for any B that we choose, there are always infinitely many combinations of lambda squared and mu squared, such that this equation holds. And so that means that there are infinitely many combinations of lambda and mu that we can choose here. And so then there are infinitely many matrices of the form lambda A plus mu B, for which its square is equal to the identity matrix. Yeah, and that's it. Sorry, I forgot to like ask everyone if they had questions. But yeah. But yeah, that's it from me. But if you guys have any questions, feel free to ask in the chat. Did everyone just leave? I'll just stop streaming now.